This. This is John Whitaker for the Probability Graduate Level class, and this is our 24th video lecture. And today we're going to do two examples, and that will be all that we do, where we're using formulas to calculate certain probabilities and expectations using conditional expectations. And so they're lengthy examples, and it emphasizes, these examples emphasizing the benefit of conditional probabilities or expectations. But also, it also kind of shows the need to be able to condition on the right random variable too. But here's the first example. It says an automobile insurance company classifies each of its policyholders as being one of these types. Okay, the types are I, where I runs from 1, 2, 3, all the way up to K. It supposes that the number of accidents type I policyholder has in successive use are independent so these are independent Poisson random variables with mean, so this is the parameter, lambda sub I, again, I runs from 1, excuse me, all the way up to K. The probability that a newly insured policyholder is type I is P sub I, where the sum as I runs from 1 to K of P sub I, well, that must be equal to 1. So the P sub I's are the chance that a newly insured driver is of type I. And then we have information about the likelihood of having, or the likelihood of the number of accidents the policyholder has in a given year. Okay. Given that a policyholder had N accidents in her first year, what is the expected number of accidents in her second year? That's one question. Okay, so here one thing to notice is that I don't even know what type she is. I just know how many accidents she had. Okay? There's a second part to this question. So the first part is about the expected number of accidents in her second year. And the second part is what is the conditional probability that she has an accident in her second year. So there's two questions here. So for the first question, is what's the expected value of the number? Well, here we'll let n sub 1 equal to the number of accidents in her first year with the insurance company. N sub 2, let equal to the number of accidents she has in her second year. And I'm going to create another variable that's involved in the problem, or something of information that's of interest. We're going to let t equal to the type of policyholder she is. Okay, so the first question that was asked of us is really this. We want to compute the expected value of n sub 2 given n sub 1 equals to, she had n accidents. Her first year, we want to know what's the expected value of her second. Well, what I'm going to do is I'm going to introduce a second variable. And so I want to recall a formula, and in the formula I'm going to recall that we're going to use is a formula that we had just written, and I'm only going to recall it for the discrete case. So here, we will compute by conditioning on t as well. And so the formula I'm going to use is, let's remember that the expected value of x given y is the same thing in the discrete case over the sum over all w's of, here it was the expected value of x given y and w times the probability, or so here it was f of w given y, w given y. Okay, so that's what we have. All right, so it's that formula I'm going to use, and t is playing the role of w, and x is the role of n sub 2, and y is the role of n sub 1. So the expected value of n sub 1 given n sub 2 given n sub 1 equals to n is equal to the sum over all, I'll say, j's, that's well right, j run from 1 to k of the expected value of n sub 2 given n sub 1 equals to n and t equals to j. And then this is the joint PMF of here it would be t given n sub 1. So this is the probability of t equaling to j, or n sub 1 equaling to n, and t sub j equaling to or not t sub j, just t equaling to j. This is a conditional PMF, so it's divided by the probability that n sub 1 equals to n. Okay. Now, the first thing I want you to recall about the problem is that n sub 1 and n sub 2, because they said that there are independence between the number of accidents between successive years, that those two random variables are independent. And what that leads us to is to be able to rewrite this as the sum as j runs from 1 to k of the expected value. In essence, what n sub 1 is doesn't matter. So it's n sub 2 given t equal to j times, and here, we've written down what I want to have written down here. So I'll just leave it alone. So this probability that n sub 1 equals to n. I'm going to rewrite that. I'd like to leave it in a different form. That's the probability, the back form, it's that t equals to j given n sub 1 equals to n over the probability that n sub 1 equals to n. So let's rewrite it in terms of the conditional probability form. I'm sorry, I didn't write this right. It's this. Put it in that. Okay. So here, this expected value, because of the fact that we know t sub j, t equals to j, so we know that they're type j. The expected value of n sub 2, that is a Poisson random variable with mean, that's what we're talking about here. So I put myself in position that I know t is equal to j, she's type j. So its expected value is lambda sub j. And now we have times the probability of t equal to j, given that n sub 1 equals to n. Of course, this is sum as j runs from 1 to k. We're not going to get a very nice closed form, but we get some way of representing the answer with summations involved. Now, the probability that t is equal to j given n sub 1 equals n. Well, what I want to tell you is that really, given type given the type, we could say the probability that the number of accidents they have in a given year. Okay? And so this is backwards from what I want. And so what we have to do is we have to switch this. And so the way we switch this should be the probability that n sub 1 equals to n given t equals to j times the probability that t equals to j, all over the probability that n sub 1 well, I'll rewrite this as using Bayes' theorem. That's what I'm using here. As this is going to be a sum by the total law of probability. If j runs from 1 to k of p sub n sub 1 equaling n given t equals to j. Okay, where j changes. So at this second, it's this j. Maybe I should rewrite this with an I. P of t equaling I. I think that's what we have. So that's where we have that generalized, the generalized version of Bayes' theorem. That's what I'm using. Okay, now the top, we're saying j is kind of like a fixed number. So the probability, given that she's type j, the probability that n sub 1 equals to n, well, this is a Poisson distributed random variable. Well, its parameter is going to be lambda sub j, so it's e to the minus lambda sub j. Here this would be lambda sub j raised to the n all over n factorial. Now the probability that t is equal to j, we had an indice here. This is p sub j. And this is over this sum. Okay. Okay. What this is going to be every time is I runs from 1. Okay, so make this change. This should be an I. Okay, so I runs from 1 to k. This is p. Well, if I know that we have the I equivalent, it's going to e to the minus lambda I to the n all over n factorial. Okay. And then times the probability sub I is equal, that's p sub I. That's what I would write. Now the top, I'll leave alone. Well, I'll leave all of this alone. That's where we are. Okay. So, here's what we have. The expected value, this is our problem, of n sub 2 given n sub 1 equals to n. What that's going to be equal to is a sum as k runs from 1, I'm sorry, as j runs from 1 to k. Lambda sub j, and then this quantity. So this is e to the minus lambda sub j, lambda sub j raised to the n, times t sub j, all over n factorial, and that's divided by, so this sum I'll write a little bigger, that's divided by this sum here. That's the sum as I runs from 1 to k of e to the minus lambda I to the n over n factorial. That's where we are. So we're using that formula to start off with that we had last time, where we had the addition of inclusion of another random variable, that just gives us more information to work with. That's where we are right now, using that. And Bayes' theorem. So this is equal to the sum. Well, this part right here doesn't depend on J, it depends on I. So if you will, this is the sum of the top. And so if I simplify that, sum is J runs from 1 to K. So the bottom of the previously big sums, what I was saying, doesn't have any J's in it. So it's a constant. We could just pull it out. So the sum just applies to the top. And so it would really be lambda sub J, so n plus 1, e to the minus lambda sub J, excuse me, times p sub J, the probability of being type J, over, this had an n factorial, so I'll pull out the over n factorial, excuse me. And then here we have this sum as I runs from 1 to K of e raised to the minus lambda sub I. Here it's lambda sub I raised to the n. And then it had a 1 over n factorial, which I'll pull out in front. Okay, so this is equal to the sum as j runs from 1 to k of lambda j to the n plus 1 e to the minus lambda j p sub j. These 1 over n's cancel with each other. Sum as I runs from 1 to k e to the minus lambda I. I forgot something here, I think. I need p sub I here. I forgot it in the previous step too. So let's move back. I'm sorry. So right here, when I did this bigger sum, and I had the smaller sum in the bottom, it needs a p sub I. That fell right down. And so here, as we make the change here, there's the p sub I, and p sub I is down here. And that's a form of our final answer, okay? That's what we write. That was only part of the problem. So for the second part, we're considering the probability n sub 2 equals to m, given that n sub 1 equals to m. Okay. That can be shown to be equal to the sum as j runs from 1 to k of the probability that n sub 2 equals to m, n sub 1 equals to n, and introducing the t equals to j, that's in the given part, times the probability that t equals to j given n sub 1 equals to n. What that is. And you can quickly see this, or maybe not so quickly, but really it's involving summations, okay, and the definitions of conditional probabilities, the joint conditional PEMFs are involved here, okay? So you see that you get the exact right thing if you multiply those out. Now, what I want to say here is this is a conditional PMF, okay? And so you can rewrite it in terms of this sum. And the sum will take care of the t sub j's, okay? So check it out. That's what it is. That's equal to the sum as j runs from 1 to k, p of n sub 2 equals to m, given t sub t equals to j, times, okay, that's due to the independence, again, between n sub 1 and n sub 2, times the probability that n sub 1 equals to n, and t equals to j, given t times. Here I'm using Bayes' theorem. T equals to j over, again, we're going to have that sum as, I'll write it down as I runs from 1 to k, of the probability that n sub 1 equals to n, given t equals to I, times the probability that t is equal to I. That's equal to the sum as j runs from 1 to k of the probability that n sub 2 is equal to m, given t is equal to j. But I think I should make more progress on this. So I'm sorry. Here, we should know what this is. So because I'm being told that the type is j, and we're being asked the probability that n sub 2 is equal to m. Now I know n sub 2 is a Poisson distributed random variable with parameters, well, it would be L or lambda sub the type. So what I would get is e to the minus lambda sub j, lambda sub j raised to the m over m factorial. This part right here we've already worked with. This is e to the minus lambda sub j for n sub 1, lambda sub j to the n, all over n factorial. And this is times p sub is j. And then this is all over. Here we've done this. This is sum as I run from 1 to k. This part right here, again, is exactly what's written here. So it's e to the minus lambda sub I raised to the n over n factorial. And then this is p sub I. All right, and so this is a constant with respect to j. So I can combine these to get, if you will, it's a 1 over m, it's factorial is what I see right there. I'll pull that out. Sum is j runs from 1 to k. This part is e to the minus lambda j. Here's another e to the minus lambda j. So that's e to the minus 2 lambda j. This would be lambda sub j raised to the m plus n, p sub j, all over. I pull out the 1, this has an n factorial here, which I put here. And then this is all over, 1 over n factorial, sum, as I runs from 1 to k, here it's e to the minus lambda sub I, lambda sub I, raised to the n, p sub I, and I've already pulled out the n factorial. So this 1 over n factorial and 1 over n factorial on the top will cancel. We're left with 1 over m factorial, sum as j runs from 1 to k, of e to the minus 2 lambda j raised to the m plus n times p sub j all over the sum as I runs from 1 to k of e to the minus lambda I to the n p sub I. And so that's a form of answering about the best we can do. I want to look at one more example. Excuse me, be just 1 second. fine, you repeat it, Mike. I don't have it now, but I'll read it. It'll be through your MIS, your Sean.
Yeah, I'm going for it, you know,
Okay, all right. And if you don't get it by 1 o'clock today, come back to see me.
Okay.
All right, thank you very much. Okay, sorry. The next thing that I'd like to do is an example. It's called a list model. It'll take me a second to get it up. I'm very sorry. I interrupted you. It's called a list model. And here's what the words say. It says, consider n elements. So here they are, e sub 1, e sub 2, all the way up to e sub n, that are initially arranged in some ordered list. Okay. At each unit of time, a request is made for one of these elements. Say E sub I. Okay? And that's whichever element can be requested, that's being requested, independently of the past with probability. So for each one to be requested, for each individual one, it has a probability of P sub I. After being requested, so once something's requested, the element that's requested, so the element is then moved to the front of the list. Okay, so it's moved to the front of the list. Okay, we want to find the expected position of the element being requested after this process has been done for a long time, has been ongoing for a long time. Okay, so here's the solution. So we got this list, it's got n elements in it, there's some order, and then people start requesting them. The chance that a particular one is requested is E sub I when it's requested, its probability P sub I, and they're independently requested. Okay, and so question is what's the expected position of where the next one's being requested? Where would it be? So we don't know which one's being requested. We don't know what position it's going to be in. And so here's the solution. To compute the expected position of the element requested, we will condition on which element is selected or requested. Because I know information about the elements that's selected. Okay, so here's what we have. The expected value of the position of element requested. Now, what I'm going to use here, so just as a parenthetical expression, let us remember that the expected value of, well, I'll just write it out. This is equal to the expected value of the position of the element requested, okay, given EI was selected, requested. Okay. So here I am using that fact, okay, that we had proven that the expected value of x is the expected value of the conditional expected value of x given y. That's what I'm using. Okay, and so that's equal to, so sum, so this expected value, I runs from 1 to n. Here, this is a random variable b sub I, okay? So I would write down the expected value, so it's this random variable, of the position of the element requested, given EI was selected, okay, times, so that's my random variable, times, and then I need to multiply that by the probability that EI was selected. Requested. So selected and requested means the same. That's equal to the sum as I runs from 1 to n. Okay, so we're given that the EI was selected, so the position can be rewritten as the position of EI. Given EI was selected, now, the probability that EI was requested, selected, that's nothing more than p sub I. Now, we need to figure out this conditional expected value. So, let's look at it. Conditional expected value of the position of EI given EI was selected. Okay. What's that? that's equal to the sum of the position of E sub I, which I'm going to indicate by the index K, and it runs from 1 to n. So K is running from 1 to n. It would be the position of EI, so that's the K, times the probability, and this is the definition of conditional expectation, times the probability that position of EI, and that's equal to K. So here, this is just K, okay? Intersected, so it's this given, this conditional PMF, given, and I'll rewrite that as an intersection, that E sub I is selected, and that ends that, over the probability EI is selected. This is equal to, due to independence between the position of EI and EI, so I'll say equals sum over K running from 1 to n of the position of EI times, here, this is the position of, the probability of position of EI equaling to K. And that's due to the independence here. So this will be a product, probability of this guy and the probability of this guy, which will cancel out with the probability of EI is selected. And so this is nothing more than, well, this is K, okay? Times the probability that EI is equal to K. So that's nothing more than the expected value of whatever this random variable is, K would represent it. And so that's nothing more than the expected value of the position of E sub I. That's what we have. Remember, this right here, this move right here, so position of EI is independent of EI being selected. That's how I can make that transition. So the expected value of the position of the element requested, okay, that's equal to, so by our previous work, that's equal to the sum as I runs from 1 to n of the expected value of the position of EI times P sub I. That's where we are. We might do a construction here of the indicator tank variable. We can do a construction. So I need to get a handle on that expected value position of EI in some way. Okay, so we're going to find I sub j equaling to 1 if E sub j precedes, so it comes before, E sub I, and 0 otherwise. And this is for j being different than I. Okay, so now note the position of E sub I is going to be equal to 1 plus the sum over the j's being different than I of I sub j. So it's one more than the number of elements that precedes that particular element being selected. So, the expected value of the problem we're working on, of position, of element requested, what that's equal to is the sum, as I runs from 1 to n, that's what we are, of the expected value of the position. So that's the expected value of the position of E sub I. Well, that's nothing more than the expected value of 1 plus this sum, so j being different than I sub j, times P sub I. That's what we have. So we can do some work with that in terms of simplifying it. That's going to be equal to, so if we, the sum, so it says I run from 1 to n. The expected value of those two things being added together is the expected value of the first guy plus the expected value of the second guy. The expected value of the constant, the expected value of 1 in this case, is just 1. And then plus, here it would be the expected value of that sum, which you could bring the expected value inside. So it's the sum of j runs, whatever it does, different than I, of the expected value of E sub j. All that times the probability that E sub I will be selected. Okay. So if we multiply this out, we get, split it up into two. Let's multiply it out. So it's the sum as I run from 1 to n. P sub I plus P sub I times the sum over the j different from I, of E sub E, the expected value of the indicator function of I sub j, the indicator function of whether E sub j precedes E sub I or not. That's what we have. This can be broken up into two sums, the sum of the first, sum of the second. And P sub I, here's this sum, E sub I j. Okay. This sum I know the answer because it's the sum of all probabilities involved here, and they have to sum up to be 1. And so I'll rewrite this as 1 plus the sum as I runs from 1 to n of P sub I times the sum at j being different than I, okay, of the E sub I j. Now the E sub I j, I'll rewrite it in some words fashion. So it's 1 plus the sum over I running from 1 to n of P sub I. Now, here, this is over the sum, is j being different than I, and the expected value of ij, remember, it is a discrete random variable, and really it's nothing more, we've shown this earlier, it's the probability that E sub j precedes E sub I, that's what that is. And that's something we can calculate, this probabilities. Okay. Now, the probability that E sub j proceeds, okay, precedes E sub I can be, so here's the way of thinking of it, can be computed by noting E sub j precedes E sub I if and only if the most recent request of either E sub I or E sub j, most recent request, is E sub I. I guess I should say is E sub j. Okay? So I guess we should think of a list. I didn't say this right. We should think of a list here from left to right, and so you put it in front when it's requested. Okay. So preceding means come before. Okay. So it's E sub j this way. Yeah, that's what it is. So it's E sub j. So the probability that E sub j precedes E sub I. That's the conditional probability, it's right there, that E sub j was requested given that E sub j or E sub I was requested. Okay, we're almost done. That's equal to the probability that E sub j requested and E sub j or E sub I requested over the probability that E sub j or E sub I is requested. Now the top, for both of these to occur, that means that E sub j had to be requested, so it's probably that E sub j is requested. Over the probability that E sub j or E sub I was requested. Okay. Now these are mutually exclusive events. So this is equal to the probability that E sub j, well, what's the probability E sub j was requested? That's P sub j. P sub j over, this is probability EJ requested plus the probability that EI requested. And so that's equal to P sub j over P sub j plus P sub I. Okay. So, we're almost done. The expected value of the position requested. And that's equal to, is what we have. 1 plus the sum, as I runs from 1 to n of p sub I. Because the sum, and then the sum as j is different than I, of the probability that e sub j precedes e sub I. We just calculated that. So that's 1 plus the sum as I run from 1 to n of p sub I. And here, this is the sum. As j is different from I. That's always j being different than I. And here, this guy was nothing more than p sub j over p sub j plus p sub I. And that's as far as we can go. So that's our answer. Well, that's enough for this video lecture. Thank you very much for your time and patience.